You're muted, Professor.
Well, then we'll we'll go back slightly. We're still talking buffers, right? And again, the buffers are not really anything other than just another acid-base equilibrium. It just so happens, because of the initial conditions, right, that my equilibrium has a relatively speaking large amount of the reactant and of one of the products, specifically the conjugate, right? And because of that, my equilibrium position is largely determined by those large amounts of the conjugate pair, right? In and of itself, right? It's just a regular old equilibrium with slightly different initial conditions, right? But because of that large, relatively speaking, amount of the reactant and product, it does have the interesting and also useful property that it is hard to move the equilibrium relative, right, to an equilibrium, a more normal equilibrium, where I'm only starting with an acid or a base, right? If I have just acetic acid, I have a small amount of hydronium and a small amount of acetate, right? And so if I were to throw another acid or base into the mix, which we'll do in a little bit, it's easy to swing that equilibrium, right? Or more specifically, it's easy to change the pH, right? On the other hand, when I've got this big initial amount of acetate, I have far less hydronium because my equilibrium constant hasn't changed, right? So my initial pH is different, but because the equilibrium is largely set by those two big amounts of the conjugates, right, it is much harder if I add a little bit of acid or a little bit of base to swing the equilibrium, or again, more specifically, to change the pH. And so the buffer is useful if I have a situation where I do not want the pH to be changing. Right. There's a very common buffer you possess. Anybody know what it is? Yeah, blood, right? If you've ever watched any medical drama, and who hasn't, somewhere in their list of diagnoses, they always refer to acidosis. Right? What's acidosis? It's your blood becoming more acidic than normal. Right? A lot of your body chemistry is pH dependent. And so it would be unfortunate, if salt and vinegar potato chips changed the pH of your blood, because you would suddenly be slower or faster or cramping or whatever. Right? And so blood itself is buffered to prevent simple shifts in pH, right? And so, there's a biological example of where this is useful. It's also useful industrially if I've got a reaction that's pH sensitive, right? One way to control for that variable is to buffer it so that even if there's other acids and bases involved in the reaction, they can't easily change the pH, right? And where we sort of ended up on Monday is because of this dominance of my initial conditions, I've got this sort of shorthand way of solving a buffer problem called the Henderson-Hasselbach equation. It's really just the Ka equation, right? And so even though, I love to say, and it's true, all equilibrium problems have the same three parts, this is still true. This just happens to be the solution to one of those parts. It's just the log of the Ka equation, right? By itself, it doesn't help me any, in that the log doesn't make it easier to solve. Where it helps me is if my good old assumption works, I can use my initial concentrations to solve for the pH, which really short circuits the problem, right? And as we saw in the case of acetic acid and acetate, and it is generally true for buffers more so than your average Ka or Kb problem, the assumption tends to be good because, again, the whole point here is I have these two relatively large amounts of the conjugates, right? And so the X is more likely even to be small here than it would be for a straight Ka or Kb, right? If it weren't, it really doesn't make my life easier, right? Because technically speaking, since my Henderson-Hasselbach equation is the Ka equation, it really should be the equilibrium concentrations of all of the species, right? But if my good old assumption that X is small were to work, I can use the initial concentrations, which actually, sadly, seems to short circuit my normal three-step approach. There is no reason I ever need to use the Henderson-Hasselbach equation. Personally, I almost wouldn't even mention it, except, of course, it is all over the textbook and all over the internet, right? Because, you know, it does require me to recognize I have a quote-unquote special thing, a buffer, and there's my solution to that special thing. But, of course, the problem is it's also an equation that has pH in it, and so it introduces some level of confusion if you decide you can just use this to calculate pH. Right. As I saw on the Sprint Synthesis 2, some people, not you, people that are still sleeping, are prone to take any old equation you find on the internet, no matter how wrong it might be, and just apply it, right? And so, you know, this potentially confuses the issue because it becomes a special case that I'm looking for. And so, you know, honestly, you don't ever need it. So if you want to go with the same three steps, right? But it does short circuit the process if I recognize that I have a buffer, right, then I really don't even need the ice chart, though it pains me to say it. And I really don't need to write the Ka equation, right, at least in its normal form, because Henderson-Hasselbach is the Ka equation. And my solution ends up being all up here, right, in the initial concentrations as opposed to at the bottom in the final concentrations, which is the more normal case, right? Really, this is, you know, where my Ka applies. But if this is true, right, when I'm working up here, then I can Henderson-Hasselbach. And so it kind of bypasses my normal process, right? It is what it is, right? And so, you know, if I'm going to use that, I at least have to recognize that's what I have. So this goes back to what I was saying last week about it is really, really helpful to learn to think of acids and bases not as single compounds, right, but as pairs of compounds, conjugate pairs, because they always come together, right? Whether I have ammonia or ammonium, I always end up with both, right? And in the context of being a buffer, what makes me a buffer is that I have both, right? So here's another buffer problem. Again, I need to recognize it's a buffer. So returning to my normal litany of things we should always do, right? The first thing I should really always be doing is classifying. And of course, as soon as I see the word pH, I'm thinking acids and bases. And quite frankly, if you want the cheat sheet for my classification, the answer is generally speaking always acid, base, or salt, right? So NH3, what is it? Ammonia, but what kind of compound? base, and ammonium chloride, what kind of compound? Salt. And so again, this is where my mantra, right? If I have a salt or quote unquote ionic compound dissolved in water, it dissociates. So really, even before I do anything, I want to dissociate it because I really don't have ammonia and ammonium chloride. I have ammonia and ammonium and chloride and water, right? The always important but generally somewhat hidden water in these problems because, again, it's solutions of ammonia and solutions of ammonium chloride, so the water is there, right? And so, again, my tell here is really that I have both of the conjugate right initially. So, it's a buffer, right? Again, I could go through my normal exercise that we did on Monday, line up all the acids, line up all the bases, and react them all, right? But in this context, what I have is the conjugate pair chloride, which is a classic spectator for reasons we will continue to discuss, and then good old water. So if it's a buffer, right, as much as it pains me, right, I still kind of sort of need the balanced equation because I do need the Ka or the Kb for the reaction, to use Henderson-Hasselbach, but I really don't need an ice chart and I really don't need a Ka equation because Henderson-Hasselbach allows me to use the initial concentrations, right, of the conjugate pair. And so in this particular case, right, since it's a base reaction, I can use the base version of Henderson-Hasselbach, which is that the POH equals the PKB plus the log of the acid concentration over the base. Right. The ammonia is, of course, the base. Ammonium is the conjugate acid or the acid form. Right. The Kb of the ammonia is 1.8 times 10 to the minus 5. So again, the PKB is just the negative log of the Kb. Right. And again, because I have recognized it as a buffer, and because I've chosen to go Henderson-Hasselbach, right, I am using the initial concentrations of the acid and base, not because the initial concentrations are correct, right? Technically, again, it still should be the equilibrium concentrations, but I have fundamentally made the assumption here that the initial concentration is, right, the equilibrium concentration because good old X is small, right?
And we can guess that X is small because the Kb is small?
No, well, I mean, partly, but I'm mostly, quote unquote, guessing, it's a horrible word, hypothesizing that Henderson-Hasselbach applies because it's a buffer, right? I mean, even if the K is larger, right, the fact that I have a large amount of both the acid and its conjugate, or the base and its conjugate, has a tendency to shrink X. I mean, if you go back and look at the example from Monday, right, the difference for acetic acid was a factor of 100 in the X value using essentially the same concentration of acetic acid, right? The buffer by its very nature will tend to shrink X, right? Now, does that mean it always shrinks X to where it's small? No, right? You could, in fact, justify X if you want, because the X value is the POH value, right? If you actually go back and look at the ice chart that I'm trying hard to avoid here, whoops, where to go, right? So, for the acetic acid, right, I'm calculating this, it's the pH box, right? And so, if I turn my pH back into the concentration of hydronium, I can see whether or not the assumption ended up being valid. But again, this tendency of this specifically to make X smaller than it would normally be has a tendency to make the assumption more likely to work. Whoops. I went too far. Right, so my initial concentration of ammonia is 1.5 molar. Right, I did mix two solutions and therefore they're diluted. One of my other sayings that will start to rear its ugly head shortly is that if I mix two solutions, I dilute them both. Right. And so the ammonia and ammonium both had initial concentrations of 1.5 molar. And voila, without an ice chart, without sort of a K equation, I have managed to solve for the pH of my buffer. So again, Henderson-Hasselbach does sort of short circuit the process. It is, on the other hand, completely unnecessary for solving these. If I wrote the book, no disrespect to Henderson and Hasselbach, I would completely throw it out. Because again, it just becomes a special case you have to look for to know to use the special formula. But it's kind of ubiquitous, so there it is in all its glory. Yes, no, maybe. Even worse, as I sit here giving you bad habits. What's that? For a buffer, X is more likely to be small, yes. But for Henderson-Hasselbach to work, X must be small. On the rare instance where X is not small, Henderson-Hasselbach will give you nonsense. Right? And so if that wasn't bad enough, right, we had it pretty much all down to every equilibrium problem has the same three parts, and I can just routinely go through my process no matter what the problem was. Now I suddenly have this darn special case I'm looking for, so I can use my special algebraic equation, which will trick some of you, not you, the people that aren't here, into trying to use this every time there's a pH to be calculated. The next slide potentially reinforces a bad habit you might also have. And so, with many warnings attached, I point this out also, right? Again, by definition, right, all of my aqueous Ks are Kcs, which means the only possible unit I can use in an equilibrium problem is molarity, right? For a gas phase reaction, I could use atmospheres, but we don't see many gas phase reactions for a little while here. So in the context of all of my aqueous reactions, I must, capital M, capital U, capital street, I must use molarity, right? But this friggin' Henderson-Hasselbach equation actually doesn't force me to use molarity, right? Which again, will trick some of you into using moles in the K equations because I can use moles here and because some of you interpret capital M to be moles, right? And so really, 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 please, 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 it has to be molarity, and capital M is molarity. That is not the same as moles. It is in fact moles per liter. In the case of Henderson-Hasselbach, right, my log term has a molarity divided by a molarity, and it's the same solution, right? You can't have a buffer by having a base in one beaker and an acid in a different beaker, right? As a result, the volume of those two solutions has to be identical. It's the same solution, right? With the net result that only for Henderson-Hasselbach, right, I could use moles. Right. And again, this runs the risk of causing more confusion than it solves. Right. Generically speaking, I cannot use moles when solving an equilibrium problem because the K equation is a Kc and it demands molarity. It just so happens the volume cancels in Henderson-Hasselbach. Right. It would be nice in a way if that always happened, right? For all equilibrium problems, right? Not that molarity is so difficult to calculate or hard to use, right? But the thing about the moles of the compound is that they don't care about the dilution, right? And as I've been advertising and as we've started to do, right, the next couple of weeks are mostly about mixing multiple acids and bases and ultimately multiple ionic solutions together. And so with all this mixing going on, I have a dilution problem, right? Not that that's so hard to calculate, right? I can always calculate the dilution, good old M1V1 equals M2V2, or as you've seen it in biology, C1V1 equals C2V2, same thing, right? But moles doesn't care about the volume it's dissolved in. If I have 10 moles of ammonia, I have 10 moles of ammonia, whether it's in a 1 liter solution or a 100 liter solution or a 10 milliliter solution, right? And so if I can use moles itself, I don't have to worry about the dilution, which does make my life easier when I'm mixing multiple solutions together, right? But again, it only really applies to Henderson-Hasselbach. I cannot do this with your average equilibrium. And so please, please, please recognize that this is not suddenly a change in the way we solve most equilibrium problems. K equations are KCs for my aqueous reactions. They have to be molarities. I cannot use moles. But again, Henderson-Hasselbach is the exception, right? And so in the case of the previous problem, if you don't believe me, right, if I actually just use the moles of ammonium and the moles of ammonia, right, I get exactly the same answer. Right. And we will shortly be mixing multiple things together in a buffer where that can be helpful and useful. But again, please, please, please recognize the limitations of that. It only works in Henderson-Hasselbach. Yes, no? Home, folks? It's dead silent. That is always a sign of a standing ovation. I will take a moment and bow. The video's off, so you can't see me bowing, but if you're at home. So here's a solution, right? Usual question, what's the pH of a solution that is 0.5 molar acetic acid and 0.25 molar sodium chloride, right? Right off the bat, I want to say, what kind of solution is it? Not a buffer, right? It's actually salt and vinegar potato chips. Well, I mean, if you throw a potato in there, right? Because again, please, 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 the other thing to be aware of is I'm not looking for a mixture necessarily. I'm not even looking for a mixture of an acid with a salt, right? I'm looking for a mixture of an acid or base with a salt that contains the conjugate, right? Sodium chloride is a salt, table salt, right? But if I dissociate my sodium chloride, I get, unsurprisingly, sodium and chloride, right? Neither one of these has anything to do with acetic acid. This is literally just salty vinegar, right? Acetic acid in water is vinegar, right? If I throw a little salt in, I quite literally have salt and vinegar, right? It has to be the conjugate. So, right, if I've got a weak acid like acetic acid, I can make a buffer, but I need a salt that contains the conjugate base, right? We just had ammonia, which is a weak base, right? I can make a buffer out of ammonia, but I need a salt that contains its conjugate, which is ammonium. If I can put in yet another pitch for why it's useful to learn to think of the acids and bases as pairs of compounds, right? It's only a buffer if I have the conjugate pair. Right. Right. So again, you know, this part of my process remains unaffected. I classify everything, and if I have a salt dissolved in water, the first thing I do is dissociate it, then look and see what you've got. If you've got the conjugate pair, it's potentially a buffer. Although, as you will shortly see, that might not be my first assumption, depending on how many other things are in there. Right. Are we good? Yeah. Slightly different problem, right? What is the pH of a solution? That part's the same. That is initially 0.1 molar ammonia, our old friend, and 0.05 molar HCl, right? Also, something of an old friend of ours. Ammonia, of course, is what kind of compound? Base. HCl is what kind of compound? Acid. What's the only thing acids do when they mix with bases? Proton goes from the acid to the base. Now, of course, again, there's really a third thing here, right? I have ammonia, I have HCl, and I have water, right? And so, again, I actually have multiple acids and bases, right? Ammonia is a base. As we've already said, HCl is an acid. Water is both an acid and a base. So if I do what I recommend I always do, if I have more than one thing, right, is to make a list of my acids and make a list of my bases. Because every acid will react with every base, they don't really choose. And so as we saw on Monday, right, in this case, I end up with the situation where I have multiple acids and multiple bases. And so I have multiple acid-base reactions. So specifically, if I have two acids and two bases, I have how many acid-base reactions? I have 4 possible acid-base reactions. And they're all going to happen. Right. And as we talked about on Monday, that's not that big a deal because they're not all equally important. And as we've seen a little bit on Monday and even somewhat last week with the polyprotics, right, as long as their Ks are different enough, I can treat them as nearly separate, or at least as consecutive reactions. I don't have to solve them all at once. I get to solve them separately, right? And so I have 4 possible acid-base reactions. Ammonia, a base, can react with either one of the acids, either HCl or water, right? And the other base, water, can react with either one of the acids, HCl or water, right? These have very different Ks. some of which we currently know, one of which we do not, right? But I'm going to do what I did on Monday, right? I'm going to let K decide which ones are more important. If you'd like to complete the reactions, of course, the only thing that happens when an acid reacts with a base, proton goes from the acid to the base. So move the proton over and you get whatever you get, right? So ammonia, the base reacting with water, the acid, right? Water donates a proton to ammonia, which gives me ammonium. Ammonia, the base reacting with HCl, the acid, the proton goes from the HCl and I get ammonium, right? And good old chloride left over. And similarly with the HCl and water. Some of these I've seen before. Which reaction looks familiar? KW, for one, right? Here's good old water with water. So here's good old KW. I know that one. Also familiar looking. Hopefully. I've got fingers crossed. Ammonia. Could we turn that into a complete sentence? Ammonia and water, what do we call that? It's the KB of ammonia. We just had it in our buffer. One more should look somewhat familiar. HCl and H2O, because that's, well, it is a strong acid, but that's just a special case of, it's a Ka, right? An acid with water is a Ka, a base with water is a Kb. In fact, 3 of these we've seen before, right? We did the HCl problem. It is a strong acid, right? We've done Kw, we've done Kb. I actually know those Ks, right? HCl being strong, the Ka is really, really big. Again, you could find a number for it. It is preferable to think of it as being nearly infinite, lest I be tempted to try to solve it with a giant number, which makes the math hard, right? As a strong acid, that reaction is essentially going to go to completion. Good old Kw at room temperature, still 10 to the minus 14. And whoops, a little copy and paste error. The Kb of ammonia is 1.8 times 10 to the minus 5. We just used that a moment ago. The only one we really haven't seen before is good old ammonia and HCl. It is an acid-base reaction. It is, however, not a Ka or not a Kb. How do I know? There's no water. Excellent. I owe you a prize. Right? Because again, the signature for a Ka and a Kb is really the water. Right? A Ka reaction is an acid-base reaction, but it's very specifically an acid-base reaction where water's the base. A Kb reaction is an acid-base reaction, but again, it's very specifically an acid-base reaction where the base is water, or the acid is water. I may have said that backwards, right? But no water, it's not a Ka or a Kb, right? Which means my tables of Kas and Kbs don't have the top reaction in it. It's a completely different reaction, right? It is the more generic case, right? Because if you think about it, you know, if I got 100 acids and 100 bases, right, there's only 200 Ka and Kb reactions, right? Because I could take any acid and react it with water. That's 100 Ka reactions. I could take my 100 bases and react them with water. That's 100 Kb reactions. On the other hand, if I reacted them with each other, that's 10,000 acid-base reactions, right? The generic, here's an acid, here's a base, is really a much bigger set of acid-base reactions, because I'm not restricted that water has to be one of the compounds. right? And so, right, we've avoided it this long, but this is really the more general case, right? Take any old acid you want and any old base you want, I can react them. In fact, in practice, this is probably the thing I'm most often trying to do, right? It is very rare that I really want my acid to react with water. I mean, I can't stop it. And since these things tend to be aqueous, it happens, which is why it's important and why we discussed it, right? But in general, if I'm doing an acid-base reaction, I am picking an acid that's probably a decent acid, and I'm picking a base that's probably a decent base. Neither one of them is likely water because water is horrible at both of those things, right? And so this is really the thing I most want to do, right? But it is also the thing, because it isn't restricted to reacting with water, which is harder to define, right? I would need a giant table of K reactions to encompass every possible acid with every possible base, right? I mean, if you look in the back of the book, there's roughly 20 or 30 acids back there and maybe 10 bases or so, which is 30 entries. If I just reacted those with each other, right, I would have 200 entries, right? Fortunately, however, this generic acid and base is really a combination of 3 other reactions that we know, right? Because if I actually take the Kb of ammonia, right, and I add to it the Ka of HCl, right, what I end up with is the reaction I have, except there's water mixed in, right? Because here's my ammonia, and here's my HCl, and here's my products from that reaction, right? But I've got this water left over. So if I just subtract out the water, I actually have exactly the reaction I want. But the water part that's in the way is good old Kw. Water plus water is hydroxide plus hydronium, right? And so, in fact, my generic acid-base reaction is really a combination of a Ka, a Kb, and good old Kw, right? Specifically, I add the Ka reaction to the Kb reaction, and then I subtract the Kw, and I end up with exactly the reaction I want. As we saw before, when we were talking about the conjugates, if I add 2 reactions together, what happens to the Ks? They multiply, now for all the money. If I subtract a reaction, what happens to the Ks? They divide because I essentially added it upside down. And so I can calculate the K of any acid-base reaction I want from the Ka of the acid and the Kb of the base and good old Kw. Specifically, the K of a generic acid-base reaction is the K of the acid times the Kb of the base divided by Kw. Right? This works for every possible acid-base combination. Right? And so I don't really need a table of every possible acid-base combination as long as I have my table of Kas and Kbs. Right? Yes, no, maybe. I hate this particular phrasing, right? But I will introduce the N word nonetheless, right? This is sometimes referred to as K neutralization, right? They really mean the N word to simply be any acid-base reaction, right? The reason I hate it, right, is because it implies neutral, right? And so, you know, in your head, it's like, oh, pH 7, right? Which is really not, generally speaking, the case, right? But as much as I may hate it, we are bound by tradition. And so this is sometimes referred to as a K neutralization. And again, I can always calculate it from the acid and the base. In this particular case, right, an interesting thing happens, right? Remember, if you go back to my original 4 equations that I was trying to balance, right, I had a really small one. That's fine. Good old KW is always bringing up the rear. I had a pretty normal looking KB reaction, and I had this giant strong acid that has essentially an infinite K, right? And if I had gone no further, my assumption would be that the HCl reaction, it's infinite. What could be bigger than infinite? Turns out K neutralization is bigger than infinite. And so using my own special parlance that you will find nowhere else, right? Again, because you could call it infinite, but you know, the idea that it's more infinite might offend some of your sensibilities. And so rather than call it infinite, I'm just calling it freaking big, right? HCl is a strong acid. All strong acids and all strong bases have freaking big Ks, right? Essentially, they are infinite, right? The reason I go with just freaking big is because freaking big doesn't sound so infinite necessarily. And so I can be bigger than freaking big. And in fact, that's what happens with good old K neutralization here, right? If I take my freaking big Ka and I multiply it by the Kb of ammonia and then divide it by good old Kw, the K neutralization for the ammonia HCl reaction is 1.8 billion times friggin' big. Right? Or if you prefer, right, it's 1.8 times infinity. So it's more infinite. Or if you prefer, and I do, it's super friggin' big. I don't really need a number for it, right? If I'm frickin' bigger, my reaction essentially goes to completion, right? Because again, I'm talking about by frickin' big, a number that's near infinite, right? And so anything that's frickin' bigger, this is always the oddest parlance of the entire semester. But if it's frickin' bigger, it's really a limiting reactant problem. Because the reaction is essentially going to go to completion. So I don't really need the number for it because I don't have to solve the K equation because it's now really a limiting reactant problem. The only reason I go through this exercise is if I have more than one reaction that's frickin' bigger, I need to know which one is frickin' biggest, right? Because I always treat my reactions in order of the magnitude of K, right? So in this case, I don't really need the number, but it's really more a ranking mechanism, right? My neutralization reaction is super freaking big, right? Whereas my HCl, my strong acid dissociation, is really just freaking big, right? And so if I'm going to solve these reactions in order of importance, and I'm going to, the neutralization reaction gets solved first. It does have the biggest K, right? For both the first and second reaction, they're going to essentially go to completion. I only really need to solve my K equation when it gets to the weak acid or base dissociation, which in this case is the ammonia. And again, as I always say, these problems are not really harder, they're just longer, right? I've got 4 reactions that need to get solved, but I don't have to solve them all simultaneously. I write them all down. I determine all the Ks, and I just go biggest K to smallest K until things stop changing. And what you'll notice, right, is that my life is even simpler than it seems, right? Because if I'm super freaking big or freaking big, my reaction goes to completion. It's a limiting reactant problem, which means I'm going to run out of stuff, right? And so as I run out of stuff, any reaction that requires that stuff is no longer possible. And so even if I had 100 of these reactions, I said kiddingly on Monday, we should do 10 acids and 10 bases because there's 100 possible reactions. Except a lot of them are going to be freaking bigger. And so you do the first reaction, you run out of something, which means you run out of all 10 reactions for that thing. And then you do the second one and you run out of something else, which means you lose another 10 reactions. And so even if you have 100 reactions, in all likelihood, there's only 2 or 3 or 4 that are going to matter. Right. Now, when you're my age and your hair looks as good as mine, I should turn the video back on so people at home can remember how perfect my hair is at all times. Right? There it is. This is your future, ladies and gentlemen. Right? You might, at my stage of life, know exactly which 2 or 3 or 4 reactions matter. And so I don't have to necessarily write down all 100. Right? From the beginning of this problem, I actually knew the only reaction that matters. Of course, that's partly cheating because, of course, I created this problem. But my point is, I don't need to know, nor do you, right? No matter how many things I throw in the beaker, right? The same basic brute force approach works. Identify what the compound is, acid, base, salt, right? Every acid reacts with every base. I let the Ks sort them out, and I just solve them in order, right? It may take me more time to sort through, right, a few of the ones that don't really matter than if I knew immediately which one did. But the bottom line is there's no reason that there's any acid-base problem on the planet that I can solve that you can't. Right. And so I've got the first reaction in importance, right? It's super freaking big. It's not even really in equilibrium. I can still make an ice chart. It's fundamentally a limiting reactant problem. And so, you know, if nothing else, the ice chart helps me identify that. I have less HCl. It's a 1-to-1 reaction. HCl is a limiting reagent. The signature for a limiting reactant problem is that your end amount is 0. All right. And so that gives me, frankly, a solvable ice chart without resorting to a K equation, right? Since 0.5 minus X is 0, X is 0.05, so it's 0.05 everywhere. And voila, my first reaction is solved. There's less of it than the NH3. What's that? It's a 1-to-1 reaction. I mean, if I'm making bicycles and I have, you know, 100 handlebars and 10 tires, which one runs out first? Right. And so my first reaction is essentially over and done with, at least mathematically. Right. My second reaction just starts where the first one ends. And so my new combination of things is now the equilibrium or end amount. It's really less an equilibrium amount and more an end amount because it was a strong acid equilibrium, right? So check this one off your list. The next biggest K is the HCl reaction, except I can't do that reaction, right? I ran out of HCl in the first one, right? My official starting point for the second reaction is 0 HCl, right? And so I did manage in some sense to solve both my first and second reaction simultaneously, which brings me to the third reaction, which is frankly the only one that really mattered. Right. And I leave you with this thought, and we'll finish this on Friday, right? My third reaction starts where the first one ended, and hey, look what happened. I actually have initial amounts of ammonia and ammonium. This is actually a buffer, right? This is really the second way you can get a buffer. You essentially make one by the neutralization of your weak base or weak acid, right? In the first type of buffer we were talking about, I mixed a salt that had the conjugate in it. I can actually also make the conjugate by doing one of those N reactions, right? If I have a weak base with a strong acid or a weak acid with a strong base, right, I can make the buffer. And so we'll pick that up and finish it on Friday. Questions or problems? Right. And again, that basic scheme will work no matter how many things I mix together. Identify the acids and bases, react every acid with every base, figure out the K values and just solve them from biggest K to smallest K. And it does not matter if you have one reaction or 1,000 reactions. 1,000 reactions is just 1,000 single ice charts. Right. I never try to solve them all simultaneously, or at least very rarely. Okay, happy spring. It's supposed to be pretty nice out there for the next day or two, so try to get out and get some sun.
Professor, I have a question.
Yep.
So, just at the end there, I was a little confused because I thought the HCl plus H2O, you said how that reaction doesn't occur at all because all the HCl was used, right?
Yep.
So then why would the NH3 plus H2O one happen? Because wasn't all the NH3 used in the...
No.
Or does that not work like that?
No, I only, the HCl's gone. I mean, if you look at the ice chart, I stopped sharing, but.
Oh yeah, no, I see it now.
There is still, yeah, there is still ammonia left.
Yeah, I just thought for some reason that they both would be used up. And then besides that, I was wondering when the Sprint 3 would be due alongside the Sen gauges.
Well, the Sen gauges, what do you mean? I mean, they all just.
Yeah, I didn't know. I knew there wasn't any official due date, but, sometimes I feel like you like them due by, the
they
same
all
day.
just, there's one due every week. We just basically skipped that 1 week where I pushed them all back a week.
Okay, yeah, I see.
But if you go back and look, I mean, if you look at the custom calendar, I did update the dates there.
All right. Yeah, I'll take a look at that. Thank you.
And technically, I mean, Sprint 3 is next week.
Okay. All right. Thank you.
Yep. Take it easy.